I wanted to make this so that for students who weren't here and don't understand what's going on, I hope that you will watch the videos of each of the runs. So make sure you watch igneous, sedimentary, and metamorphic. Those videos that we watched in class, you are going to be needing those so that you can understand exactly how they form. He gives a lot of good visuals and does that flow chart. So after we watched the videos, then we kind of filled out this rock chart. This is your kind of like a note chart that you would put into your notebook. So this is what will be your notes. So I'm going to go through each one so that you know essentially what you should have come away learning, and then also those samples that you didn't get to see in class. And they're always on display, so you can come at any time and look at them. So an igneous rock, that's what we learned about on Monday. It talks about how when lava or magma cools down, it will form an igneous rock. But because lava, which is what's pouring out on the surface, and magma, which is deep underground, like deep under the volcano, or even in areas where you wouldn't suspect magma to be, there is magma underneath the Earth's surface. So those two locations will cool in a different way, and how they cool will give you different types of igneous rocks. So first, also, I wanted to mention in the additional info that this is what most of Earth's rocks are. So we haven't quite gone over it yet, but the Earth, when it first formed, was basically a giant sphere of magma. And so as it cooled and formed some of Earth's first rocks, they were all igneous. So it makes sense that the majority of rocks still on this planet are igneous. So it certainly makes up the majority. Okay, so let's talk intrusive. So intrusive igneous rocks cool slowly deep inside of the Earth. They are insulated by the ground. They're not exposed to air, so they will cool over thousands, if not longer periods of time. Thousands of years, I should have said. And so because it cools so slowly, the minerals inside of that magma get time to grow and crystallize and get bigger and bigger, so that eventually you'll end up with large size crystals. And that's when you will end up with granite. So granite, let me make it bigger. Granite has large chunks in it that you could actually pinpoint and see. So the pink color here, that is feldspar that grew. The opaque colors of like crystal clear that you kind of see, those are quartz. The shiny flecks that you see sparkling off this surface, that's mica. And then the little black parts on it, that's hornblende. So those are the ingredients that make up granite, and each granite will look unique and different depending on the quantity of each kind. But this took thousands of years to cool down, which allowed for those crystals to grow and get bigger before it solidified into rock. Okay, after that is extrusive. So extrusive is lava that cools on the surface. And because it's cooling on the surface, it's exposed to air and even maybe rain or water. So it will cool very fast and not give those crystals time to grow and get bigger. So every grain size on an extrusive rock will have small or no crystals at all. The examples that we did in class were basalt, this black rock. You really can't see any individual grains. With a microscope, you might be able to see some flecks, but it's not large enough that you'd be able to identify what they are. So this is basalt. This is the rock that composes all of the ocean floor. So we have a lot of basalt on this planet. The fan favorite is the obsidian. Obsidian has this glassy texture because it cooled the fastest of all of the extrusives. They cooled when when lava pours out on the Earth's surface and goes directly into water. So that water will flash freeze it. We'll have no time at all for those to grow, so it has no crystal grains at all. And hence that glassy texture is made. So this is obsidian. And last is pumice. So pumice is this like a lot of holes, a lot of gaps inside of there, because this came from a volcano that exploded outward, very violent explosion, so that it solidified in the air, and while it solidified, it trapped the gas bubbles from that explosion inside of it, and leaving behind those spaces. So there's a lot of holes inside of here, which is why it's very lightweight. This is pumice. Okay. Moving on to sedimentary. So sedimentary rocks, they form from the compaction and cementation of sediment. So if you get all the sediment that deposits down, it will compact over time because you'll have layers of layers pushing down on it from gravity over time. And then it will crystallize and cement together like glue. There's 3 types of sedimentary. The first type is clastic. I think of clastic like the classic version. It's very basic. Basically it means it's just a bunch of compacted sediment. There's no other thing to it. It is just sediment grains that have been compacted and cemented. So the best version of this is sandstone. So sandstone, and I can get up closer, you can see the gritty texture to it. So, and you can feel it if you want to find it in class, just ask me. So it just feels like a rock of sand, and that's basically what it is, a bunch of sand particles that have been compressed and compacted and cemented together. So that's sandstone. Conglomerate is the largest of the sizes because it can range in size. These would be considered like pebble-sized, not quite boulder-sized, but glued together. It is like a rock of rocks. So it is glued together, and this conglomerate was made in a riverbed. You can tell because all of the rocks are very smoothed out. Rushing water would wear them down and make them smooth like that. So this compacted and cemented those pebbles together, and that's a conglomerate. After that is shale. So shale is the smallest of the pieces of the sizes of the sediment. It would be clay particles put together. This is very brittle. You find this jutting out along the river, like the riverbeds. You can like pick them apart with your fingernail. So it's very fragile, but it's basically just clay particles that have been compressed and cemented together. So that is shale. I'm sure you've seen it if you've gone down by the river. Okay, after that is crystalline. So crystalline rocks, they grow out of a solution, and they're either going to grow from evaporation or out of a hot water solution, just like the minerals that we talked about. So this is like a rock version of the minerals that we learned about. So these are going to have, so it'll be small in grains. You really can't see individual grains, but you can see crystals. If you can see the shimmering, that's crystals of calcite. So this particular one should look familiar because this is the most common rock in Kansas. In fact, this is Kansas's state rock. Isn't it beautiful? It's called limestone. So limestone is primarily calcite. So it keeps the trait that calcite has. It will fizz with acid. So I could, on the outside of this, grind it with kind of get some powder up, drop some acid on it, and it would fizz and bubble just like the calcite because it's primarily calcite. So it's like the rock version of calcite. Limestone. After that is organic. So organic, I forgot to get, hold on, give me a second. sorry. I thought I had everything. Okay. So organic means it's still like this piece. This is still limestone. It looks very similar to the material, except this one has crystals, so it grew just from a solution. It didn't need any biological matter. But this one has biological matter because you can see the shells. So shells, since same thing as calcite, right? It grew out of the calcium from the bones and shells. So we can get limestone that grows from it. So limestone has two different ways to grow: crystalline or organic. So if you see shells or any signs of life, you know how it grew. Okay, also coal. Coal is an organic sedimentary because it grew from squished down plant matter. So from a long, long time ago, before the dinosaurs, the material on this planet was very high in carbon. And so when it deposited, it squished down over time, pile and pile and pile, squished down. The liquid that oozed out of it is our oil. The fumes that came from that area that deposited in like pockets underground, that's natural gas. And the solid matter that left behind is coal. So these are the three fossil fuels that were made, which are types of sedimentary rocks. Coal. Okay, the last one, can I move myself? Yay. Okay, the last one is metamorphic. So these are changing as a result of being exposed to intense heat and or pressure. So it's really important. Oh, I forgot really quick. It was on here, but I didn't mention it. For sedimentary rocks, in the additional info, this is the only kind of rock that you will find fossils. The process that makes an igneous and the process that makes a metamorphic will destroy evidence of life. So, we may not have the cool metamorphic and igneous rocks here in Kansas, but we have a ton of sedimentary, which means we have all the fossils. So that's cool, right? Okay, so metamorphic. The additional info for metamorphic is this process of changing can make them stronger. So these are really strong rocks. Also, it's really important you know that it can't melt. If the intense heat and or pressure applies so much to the point that it melts the rock and turns it into magma, it can't be metamorphic, because when it finally solidifies, it's igneous. So if you go too far and you melt it, you no longer have metamorphic. So that's an important thing to remember. So there's two types of metamorphic: contact and regional. So contact means that the rocks that are surrounding the magma underground, so they're not melted all the way, but they are certainly being affected by that high heat from that magma. And so it will turn it, it will become a contact metamorphic process, which will change it into a metamorphic rock. So whatever it was there before, it turns into metamorphic because it's almost like cooking it, like in an oven, making it soft and pliable so that it can warp it and change it, but not melt it. It's not high enough that it melts. So it's like kind of a cooking process. And the type of the way it looks is called non-foliated. So there's two different ways you can describe a metamorphic rock's texture: foliated or non-foliated. So non-foliated means you can't really see any patterns to it at all. It's all random. Either there's no pattern at all, or the pattern is all, every which way. So the best examples of that is marble. So marble, if you have any marble at home, you will see veins in it that won't have a direction. There's no set pattern to it. This obviously was cut, but There is no pattern to it at all. Also, quartzite. By the way, limestone, if it goes through the metamorphic conditions and turns into a metamorphic rock because it's getting intense heat, turns into marble. Okay, so this becomes this. And now this has changed so much that it won't fizz anymore. And it's much stronger than limestone. The other example is quartzite. Quartzite is insanely strong, and you can tell there's no pattern at all to it. It comes from sandstone. So in sandstone, if it was to go through intense heat but not melt, it turns into quartzite. So all those crystal grains that made up the sand, those are primarily quartz, turns into quartzite. Okay, the other one is regional. Regional means that, so we haven't talked about tectonic plates yet, but the video mentioned it. So when you have forces of plate movements pushing together and interacting underground, where they meet up is going to have intense pressure because everything is going together at the same time. That amount of pressure will also warp and change these rocks into metamorphic rocks. And its texture will be foliated, which means there is a pattern to it. You can see banding or layers on it. So the best examples, so shale, if shale turns into a metamorphic rock because it's going through pressure, it turns into this. This is slate, which is just chalkboards. But you can kind of see the layers through that process of getting pushed together in that pressurization. And slate is very hard. I would not ever be able to break any parts off of this because it's very strong. This is useful in tiles on rooftops as well as tiles on the floor, so very durable and strong. The other one is, granite. If granite goes through intense heat and pressure, intense pressure primarily, which oftentimes you're going to see in mountains, it will turn into gneiss. Gneiss, I know it's pronounced nice. It doesn't look like it's spelled correctly. It's the Gneiss. It's pronounced nice. And I have a couple samples of them. So gneiss, you get these banding. So you can imagine that band, that like white colored band, was the quartz that was inside of the granite that got pulled and squished and changed. So think of it kind of like Play-Doh. It gets warm enough through that pressure that it's able to be manipulated and strengthened, but not melted. Okay, so that's it. I know it was a long video, but that covers all of the rock types and the examples that you needed.